This conference will now be recorded.
Okay, yeah, go ahead, Ellen.
Okie dokie. Let me switch my camera on and I'm going to share my screen. I may get some noises from the apartment around me.
Okay, no worries.
Just apologies if that happens. Somebody's washing machine's on by the sound of it.
Okay, we can see your screen.
Okay. Well, let me see if I can shrink this down a bit.
Yeah, it's full screen now.
Mouse. Yeah, the only thing is I get a... Anyway, never mind. I'll make do.
We can live with it.
yeah. No, it's just my screen. I can't see the entire presentation.
Oh, I see. Okay.
Okay, everybody. Good morning. So, for those of you, I'm sure most of you know, I'm the OCP High Performance Compute Subproject Lead, and as you know from my my commentary over the various months and years, I've really got a systems architecture perspective on the whole world of compute, in particular high performance compute. So what I wanted to really do here is I've recently I'm putting most of my energy into trying to take some of our OCP HPC concepts to reality from the concepts that we've got today. So I'm putting almost full-time effort into that now. So, but from a chiplet perspective, I've often, obviously chiplets are all about chiplets on a single substrate, and I guess we've often got a little bit confused, or maybe I've got confused in terms of how I particularly see a chiplet. Like, could it be pluggable? I've often said. So anyway, today what I'd like to do is just show, just do a very quick review of what we're up to in OCP HPC. I'm hoping most of you know a little bit about it, but I'm just going to very briefly touch on what it looks like to get you a feel if you're not familiar with it. But so what I'm really taking this top-down approach of, so as a system architecture considerations when we're doing for this chiplet enablement as we move forward with chiplets. And one thing I wanted to really quote, which is something I've been thinking about for many years now, is and Google made it clear when they announced their TPU v4 details. And to quote an article on this, it said that Google's is saying that system architecture is more important than microarchitecture these days. And if you look at what they've done with the TPU v4, you can absolutely see that. And also, if you take a close look at what the likes of NVIDIA are up to with their Grace Hopper modules, etc., you can see that they are taking more and more systems directions, improving their system architecture. The only problem is all of that is being done in a proprietary fashion. So where we want to do it here in OCP in a more of an open fashion. So if we're moving forward with chiplets, can we actually think a little bit beyond the package when we think about how do we enable this chiplet ecosystem? So that's really my perspective. So I put this slide in. I stole this slide from Google, from the OCP summit in Prague, the regional summit. Basically, everything we're doing in the OCP HPC subproject is we're focused on energy-centric computing. It's all about how can we minimize energy reuse and improve sustainability. So if you're not fully aware, I've only recently become aware of all these different scopes, as they call them in the emissions. There are three different scopes. Scope 1 is really any direct fossil fuel consumption within the data center itself, like backup diesel generators or natural gas heating, as they said here. Scope 2 is what we all typically think of when we're thinking about energy efficiency of a data center, is the actual, the power consumption, the draw of electricity from the utilities, and where that energy actually comes from. And how do we minimize that consumption by more and more efficient computing, which obviously chiplets and heterogeneous processors are all making fantastic strides towards. And then finally, we've got this scope 3, which actually arguably is one of the more challenging ones, or is one of the bigger ones, is the actual infrastructure of the data centers and the computer equipment itself. And so these are the three areas. And I guess one of the focuses in Prague was Meta made a very clear statement. You know, they're putting a lot more energy into how do you improve for scope 3. So that's already the backdrop. You know, it's a way. Whenever we're architecting some of the radical ideas in the OCP HPC, which they are pretty radical, it's a case of we're putting that front, left, and center is our focus on energy-centric computing. So what we've got today, the latest incarnation of HPCM, is what we call a direct water-cooled, or liquid-cooled, should I say, could be water, HPCM concept. So I'm just going to give a brief review of that for everybody, and if nobody's familiar with it, just to set the scene a little. So I've just got this one slide. So effectively, what we've got here is, I'm hoping you're all familiar with the OAM, the OCP accelerator module. And that is very similar to NVIDIA's proprietary SXM module that they use for all of their GPUs, etc., in the data center. So it's this mezzanine module format, and the size is roughly 6 inches by 4 inches is the actual size of the board. That then will house a very powerful processor, up to 1 kilowatt these days. I think the H100 is mentioned as being around 700 watts. But we're architecting the OAM, the latest OAM V2, I believe, is trying to reach support 1 kilowatt. And so the HPCM was inspired by that, but instead of having the mezzanine connectors on the bottom of the board connecting to a host motherboard, we actually replaced it with media interconnect and cable interconnect on the back. So we actually removed the motherboard altogether. And so you can see in the top left, you can see that there's 16 EDSFF connectors, which is obviously the standard. It's becoming very popular now for SSDs and CXL.mem, and also the NIC 3.0 standard as well uses these same connectors. So we've got some sort of normalization going on here where we can plug these different media and IO modules in. But this is coupling these connectors really tightly. So we're actually using the module as like a backplane that can be populated with media, as well as on the front side, we have this very powerful processor, you know, and/or accelerator, and/or switch, etc. Okay, and then the 4 connectors around those are basically standard MCIO connectors in this particular incarnation. Which supports PCIe and will support CXL as that comes in, because that's over PCIe. But again, the idea of this module actually is protocol agnostic, but this is the fundamental mechanical electrical interconnections. So in the bottom left, you can see a bunch of E3.S and a NIC 3.0 populated in the module, with one of them open. That was an OMI one that we designed when I was with OpenCAPI. And then as you look to the right, you see the orange enclosure, which is effectively the water-cooled enclosure. Now we're innovating a little bit more around the water-cooled enclosure, but the idea is that everything is actually directly water-cooled. There is no air. In fact, ideally, you would be insulated from the air, and the only way out for the heat from all the devices would be through the water. So you get an efficient transition into the water cooling. And so here you can see on the orange module and on the green one at the top, you can see there's a couple of power pins. So that's going to bring 48 volts in. So that's given us a very efficient path for the power in, compared to coming through motherboard power planes. And we've got water connections there for actually. So this module is these connectors are blind mates. So you would effectively plug this module into a wall, and then you would plug hundreds and thousands of these modules into one huge wall in the data center that would replace the 19-inch rack. So that's the very basic concept, and you would cable these modules together. You could have switches in some of the modules, so you could build a classic architecture, and it could run a classic software stack, or you could build very custom ones as well. But you can wire all of these modules up for a domain-specific application, mixing and matching heterogeneous processors from different vendors as makes sense. So that's basically what we've got as a technology. One of the areas that we're driving to get interested in this is that this would be a very good enablement platform for CXL. And so, we're seeing a lot of these media modules from Samsung and Micron and the likes supporting the CXL.mem, and we're seeing devices from various customers, various suppliers supporting the CXL host connections as well, etc., and switches. So that's one area that we're actually looking at. So I've already touched on this, but basically, in summary, the HPCM is focused on energy-centric computing. So from a scope 1 perspective, we want to reduce the operational emissions of direct consumption for heating buildings, etc. Well, the actual energy reuse from the hot water coming out of these devices is going to be a lot more easily reusable than some of the other implementations. On scope 2, we've got the lower power consumption, so we can get some dramatic improvements. And if you look at the Google TPU v4, again, there's some really interesting innovations there, where when you're building a domain-specific computer, you can control the wiring, do less switching, and save some tremendous amounts of power. You've got less potential, we've got less data movement because things are much closer together. We've packed an entire server with lots of memory and storage all into a small module. So we have an opportunity to save power there. And we have far more efficient power delivery as well. We're improving that power delivery path, which is ever essential. And as far as scope 3 is concerned, we're actually, again, by making this a really small and dense module and densifying everything, we're actually going to be using less raw materials. So from a sustainability perspective, we win out there. So that's the premise of what we're trying to do. So it is very radical. So we've got to change everything. We've got to smash down the silos, and it's a big challenge. Right? So that's what we're trying to do.
Alan, maybe one question just for,
yep.
I guess maybe that already answered, like the dimensions of this orange box, like just, I have no concept how small or big this thing would be.
Yeah, so I did just briefly mention, but I'll come on to it on the next slide, but it's based around the OAM module size, which is 6 inches by 4 inches is the size of the PCB, or gotcha. 165 millimeters by 102 millimeters if you're metric.
Okay.
So yeah, this slide shows this. So the first thing I wanted to highlight here is these chiplet packages are getting pretty damn large. If you've been tracking, I think AMD's EPIC is 78.5 millimeters square for the package itself. Now I've just shown a generic sort of chipletized package here, just to get the point across. And if you stare at it and you actually put this on top of an OAM or an HPCM module, you can see that they're beginning to converge in size. Now, the other thing to realize here is these OAM, these mezzanine modules, NVIDIA's SXM, OAM, and what we're trying to do with HPCM, they're becoming more and more popular. And if you stare at them long enough, all they really bring is the power delivery to this powerful packaged chip, and highly, very high performance, very good signal integrity interconnect to it. And if you look at what that replaces like a CPU going into an LGA socket in a big motherboard, right? And when you ask yourself, why was that done? NVIDIA can probably give you a lot more reasons than I can, but what becomes obvious if they soldered down the chip into this mezzanine module, to get rid of that horrible LGA connector from a signal integrity perspective. They've got far better ability to cool the module and power the module compared to a PCI card, which is what the GPUs used to be in. But effectively, we've got here quite a sophisticated packaging around a packaged device. So the question is, and if we look at it from Yes, so the mezzanine modules are really just bringing power and interconnect, wrapped up in a nice pluggable module, which is good from a signal integrity perspective. And you may have a little bit of clocking and a little bit of sideband, but that's fairly minimal in comparison. But when you look at the OAM module, for instance, the transceivers have a loss budget allocated for the entire module of 8 dBs. And when you peel back that onion a little bit, basically there's 5 dB allocated to the package and 3 dB allocated to the PCB and the connector. So that's 8 dB of what is typically a 30 dB channel that you want to communicate across. So if you've got two of these modules talking to each other, you've used over 50% of the channel budget just getting off the modules and back onto the modules. And then you've got about 14 dB left to traverse those modules. Now, for those of you that know OAM, this is where it really hit me across the face. The universal baseboard that the OAM modules sit on, they have a liberal spreading of retimers just to get across the backplane to the PCI switches, or even to get into the QSF PDD modules for fabric expansion. So you can see that we're running out of budget as these speeds get higher, and retimers we really would rather not use them. They add latency, they burn power, they take up real estate, they cost money, and they add no value. So we'd rather not use retimers if at all possible. Okay, so that's an observation. Also, power integrity is becoming more and more challenging, and we all know that if you look at any of these packaged devices, the capacitors have been sucked onto the package as well. So we're getting closer and closer to sucking the power on the package, and we know we need to do this for chiplets. So the conclusion is, why not make the module the substrate and then remove the package altogether? And so cut out the middleman. And then we've got this, so we get rid of that horrible solder ball, which is a bad signal integrity part of there, as well as some of the others. Now, the challenge with this is a very large substrate now, but I've talked to many people over the last few years about this, and most recently Fraunhofer and IBM, some of their substrate specialists, and someone else, and it looks like people are saying it's not impossible, and it seems relatively viable, and it seems like this is an area that we're going towards anyway. So why not do that? Is the idea. Okay.
So then you're basically saying that that new board would be the same complexity as the package itself now, like in terms of, say, like would also be, say, like some like many layers ABF type substrate, for example, just even bigger now.
Right, you'd bring the HDI of a substrate, where you basically make the OAM PCB into a substrate material with the standard stack up there. Obviously, the boards are thicker, so there are, like I said, there are challenges. But yes, effectively, you're giving all the substrate geometries. So this is organic, by the way. I'm not talking about advanced packaging. This is organic. So the 130 micron bump pitch or something like that is what we're assuming. Okay, so answer the question. Okay, so if we sort of think along those lines then, and we think that the HPCM could be actually a chiplet substrate, and when you think about it, this is a standalone module which can be plugged into media, and cables can be plugged in to wire it to other modules. You can build a system. It becomes quite an interesting chiplet enablement, or it could become an interesting chiplet enablement platform. So one of the first things that crossed my mind, and I don't know if you guys are thinking about this, is if we have some sort of potentially standard tile chiplets, like if a chiplet is this small, it can have so many bunch of wires ports on it, and you can put it next to a bunch of other chiplets, or you could make a bigger device if you had a bigger monolithic device, but then it would have more bunch of wire ports around it. We could almost have a Lego block approach to putting people's chiplets down on what could be a pre-routed substrate. So it could be a substrate with a bunch of little links, and depending on what size Lego block tiles you put down, you could mix and match and connect big and little chiplets together. And as long as you obeyed the rules of less than 25 millimeters apart, based on the bunch of wire spec being able to have a reach of 25 millimeters, we should be in good shape. Now, if you just a minute, let me make sure I'm not right. And what you could potentially do there is we could actually place the I/O tiles actually quite locally to the interconnect that they're going to be launched out of, the connectors on the back of this module. And so you can see around the periphery, you can see I've dotted a couple of chiplets that are basically where the connectors are, and also the ones in the middle have the smaller chiplets on the left and the right. And that's just sort of to give an idea that you could actually get the locality of the chiplet close to the I/O piece where it gets launched into a cable, and whilst not violating the 25 millimeter rule of the chiplets. And finally, we'd get improved power integrity, because that's basically all in the stack up. So you can improve that as well in the module. So that's the premise of the idea. Any more questions on that before I go on to the next piece?
Question, Alan. So what is the total power budget that you envision for this module?
Yeah, good question. So we basically took the OEM direction. So we'd like to power up to 1 kilowatt for the main processor or the group of chiplets that we see here. So about 1 kilowatt there, and then we're assuming that the single width EDSFF modules, the E3.S have a budget of 25 watts, I believe. Now we potentially could call more than that, but if you assume 25 watts times 16, I believe it comes out to about 1.4 kilowatts for the module itself, for the powerful processor, and so 1 kilowatt for the powerful processor and 400 watts for the media devices.
And you are envisioning that the carrier, the green carrier that you're showing, will be one carrier that's of the size of 165 by 102 and can
Correct,
potentially house all the chiplets.
That would be the idea, yeah.
And would you imagine that these are super fine pitch die-to-die interfaces, or can they be?
Well, so it's organic is what I was assuming. So you're 130 micron or thereabouts.
Yeah.
I wasn't thinking advanced substrate.
Okay.
I was thinking that you could, and obviously there's lots of different ways of doing the advanced stuff like the EMIB, etc. But if you had a standard CoWoS, you could potentially have a CoWoS die with all of the chiplets, advanced chiplets on top, and then you could mount this onto this as a package substrate instead of putting a CoWoS into a normal package. So you could potentially do that.
Yeah. So there is one technical issue that is more based on the current state of the art. That is, the organic packages typically today are yielding in the range of, say, 80 by 80 micron. That's why you see those sockets. They are in that range. Yielding organic at 102 by 165. Haven't seen anything. We've definitely seen packages in 100 by 100, but that doesn't mean that there wouldn't be a technology. I'm sure there will be some technology that can support it.
Yeah, so I've spoken to a number of people over the years on this, and you're absolutely right. But it seems there's a couple of things. I think in the early days of ODSA, there were a bunch of substrate startups that were, or maybe established companies that were showing their view of a path to a substrate of a decent size. Speaking to some experts that I used to work with, they had various comments like, as long as your routes were local and it didn't go across the entire substrate, you could actually manage them quite effectively without any breaks in them. But again, I'm no expert in this area, but I talked to Fraunhofer, I talked to IBM, and I've talked to somebody else, and they all basically they all said it wasn't. It's not a big R, big research, little d. It's more little research, big D. And so it feels like it's doable. And then when you see that these packages that exist from like AMD EPYC, they're getting up to this size already. And so they're having to deal with these challenges anyway. But by the way, in terms of CHIPS Act, I understand that only 5% of substrates are made in America and 95% are made in Japan and Taiwan. So that's one thing I'm hoping the CHIPS Act is helping us to deal with. And this could be an area that we could focus on. So yeah, it's not a slam dunk for sure, but it doesn't seem inviolable right now. It's as far as I can see from the experts I've spoken to.
Yeah,
Alan, sorry, I had a quick question. Could you have two of these organic substrates in some sort of a carrier as a sort of an interim process where you could do sort of have some sort of a retimer capability, but much less power and latency than the traditional retimer for sort of, which would bolt onto something of this size. I don't know. I'm just trying to think out the box.
Yeah. No, Cash. You're spot on, right? This density of packing opens up the potential of what I called chiplets being connected. And so let me come on to that on the next couple of slides, because hopefully that will become a little bit more make a little bit more sense. But in short, if you look at these little chiplets that we have, they're very close to the interconnect that they're communicating with. The interconnect could be an active cable, and it could be a bunch of wires interface across there at 0.5 picojoule per bit, but because it may be less than 25 millimeters. So we could
Alan, NVIDIA just did a paper where they did 50 gig across, using I guess an XSR or whatever. I don't want to use that particular term, but that was talking about 0.3 picojoules per bit, right? So
yes. So that was a Grace Hopper where they had the Grace package right next to the Hopper package, and it was 1.3 picojoules per bit for them to go, compared to a PCI 7 to 10 picojoules per bit.
Right. So there's obviously, with some innovation, a capability to go. That was a very short distance to get that power, right?
Yes.
I just saw the announcement a couple of days ago. So, but there's definitely. I think being able to connect two modules, assuming the organic area is a little large right now, if you could just go half of that, that seems more reasonable maybe. And then obviously some methodology to connect them. And it does look like the SerDes guys. Once one does it, then there's going to be 5 other guys doing something similar, right?
Right. Exactly. So if you look at NVIDIA, their NVLink, I think they've got 4 or 5 different PHYs for these different reaches, from chiplet to package to package. Exactly. And by the way, that's really the whole idea of these modules. If you look at the proximity of these media modules with their controllers to the big chip, you're in the region of 5 to 10 dB apart. IBM kindly did a simulation for us, and we were sub 10 dB for PCI Gen 5. We were I think it was about 7 dB if we unpackaged the chip, the processor chip, and put it down on the substrate on the OEM.
Yeah, no, top down, it makes perfect sense. I was looking at it from the bottom up. I think the bottom up technologies are also, they're a couple of years away, right? From becoming much more common, I would expect, right? Of being able to connect across, two modules that are very close together on some carrier or some other more traditional substrate. I mean, I don't,
Yeah. So well, the other thing here is once you've got one of these modules, you start to populate these modules. So you'd have one directly next to it. You'd have one north, one south, one east, one west, one northwest, one. So basically, you build this wall of compute with these modules, and then you can have short hop cables between the modules if you want direct connection. And those also could be lower energy. Well, but one of my main points here is actually that I didn't really emphasize is I was saying that OAM, you need 8 dB to get off the module. So therefore you use over 50% of the 30 dB budget to just communicate between the modules. If you put these little IO chiplets directly over the high-speed connectors, we can probably get to less than a dB to escape the module. So we're saving 7 dB, or on a channel between two modules, we're saving 14 dB that we could give back to the electrical cable to either do longer distance routes with copper before we go optical, or reduce the power for going shorter distances to the likes of 1 or 2 picojoules per bit to drive a short link between two modules. And so that's what this opens up. By densifying everything, it opens up the opportunity to save energy. But this is at the pluggable level. One of the big challenges of chiplets is we've all got to spend $1 million putting a bunch of chiplets on the same substrate. Whereas if you could make some of these chiplets pluggable, maybe with a picojoule per bit or 1.5 or whatever, then suddenly it allows me as a systems engineer, as a one-man band wanting to build a special purpose computer, to just buy the bits, buy the active cables maybe with the chiplets in them, and plug it together very quickly and very cheaply without spending $1 million on my preferred packaged set of chiplets. And so that's the sort of top-down thinking that I'm trying to do here.
Alan?
Yeah.
So the question is, all the connectors are on the backside of this.
Correct.
Right? So
Correct.
have you looked at, and you mentioned something about having the IO chips over these connectors,
Yeah.
but if this, at least in this cartoon, you're showing one central larger chip, or it might be multiples.
Yes.
So connecting from that over to the IOs, have you thought about what that might look like, and if there are any particular...
So I'm assuming that's a bunch of wires interface from one of these edge chiplets to the IO chiplets, right? So, but it needs to be less than 25 millimeters to obey the spec, right? So I was assuming it would be a bunch of, it would be a bunch of wires to an IO. So the IO tile could change from Ethernet to PCI, whichever you want to be communicating over, if that makes sense.
Right. That I understand. I was trying to understand in terms of bandwidth, is it one bunch of wires slice, or it's going to be 4, 5?
So it's in terms of bunch of wires version 2, everything I've done on here, these connectors are 8 transceivers, these topology connectors on the edge. So they're 8 transceivers. So we're assuming, if you assume PCI, then you'll be at 32 gig today. So basically you would have an IO chiplet that would support a single bunch of wires interface with at 32 gig or UCI.
Okay.
Okay, so let's just delve in a little bit more into this interconnect. So then we've got the silicon photonics. So one of the things that I've always been thinking about is, we've got this world of co-packaged optics that we're moving towards. We've talked about near packaged optics, and we've talked about electrical. We want to stay electrical as much as possible. It's cheap and effective. And so how do we support this transitioning world? And that's one of the main things that I've been interested in is, we've got this holy grail of co-packaged optics, but it's going to be a long time before everything, including SSDs and memory, is going to have an optical interface. so we need to think about this a little bit more from a system perspective. So again, now this is where I'm really out of my domain. I'm not an expert in this, so this is very much PowerPoint. So feel free to tell me I don't know what I'm talking about, because I probably don't. But anyway, reading a paper, and I have worked with silicon photonics over the years, but really as somebody, a systems guy looking in without any detailed expertise. So I understand there's these different mechanisms where silicon photonics has been constructed over the years with the photonic chip and the electronic interface chip that goes with them. I'm just looking at this particular one as a co-packaged optic, and I call it version A, co-packaged optic A, that we could maybe implement on our now HPCM substrate. And I've got co-packaged optic B of, well, maybe we could actually on the top and bottom of the PCB, could we actually mount the photonic on one side of the PCB and the electrical on the other side of the PCB as a co-packaged optics B variant? And hopefully this will become a bit more obvious in a moment. And so this is now staring at the bottom of the module, so you can see the 16 media connectors and the 8 topology connectors on the outside. And you can see that I've labeled them. Just the one on the top left is MCIO electrical, standard 8-lane PCIe CXL 8-lane IO. Then I've shown, which you can't really see, but an MCIO electrical with what I've called a near packaged optics active optical cable. So you can just sort of see a green PCB in there with some components on it. And then I've got co-packaged optics A, where you've got a little hole in the connector where the actual photonics can come through. And I'm not sure if any of you ever remember back in the day, Intel did introduce a USB interconnect where they actually had a couple of optics on the back of it. So you could actually either electrically plug in a USB cable, or you could plug in an optical fiber cable and pick up some optics if you had an optically enabled USB. This was pre-USB-C. And so that's sort of inspired by that idea. And then we've got co-packaged optics B with the same little hole. So effectively, what we potentially could do is we could support, this standard could support, or hopefully support, all of the above interconnects, co-packaged, electrical, or near packaged. And depending on what you implement in your module, you can provide all of them or some of them. So that's the idea. So let me just switch gears here. And I just want to go to the actual model itself. So here we're looking at the actual, there you go, I can reduce this down a bit now. There you go, that's better. Okay, so here we can see the overall module, and here's the top. So what here, this is the electrical one, or maybe this is the electrical, sorry, this is the electrical one, because it's flipped over. So this may be your, we were already talking about, your little IO chiplet that's directly below the connector, and that less than a dB, and then you've got another 29 dB for the cable itself, and the cable's very efficient compared to PCB routing, so you could probably get many meters of distance even on the thinnest gauge cable. And then we've got another electrical one here, but we've got a near packaged optics active optical cable plugged into it. Here we can see that we've got the stacked optical die and electrical die all mounted on the top here. And one would assume that the light would be launched out of the back of the optical die through that hole that I showed you. And here we have just the electrical die. And so if I just switch over now, if I go into the model, we look on the connector side, and again, you can see, now it's on the bottom here, you can see the little hole bringing the light through on these. On this one, you can see I've got a little paddle card PCB plugged in with the optics chip on there for an active optical cable. And here is just a regular electrical interconnect. So that's that. If I just peel these off a moment, let me just hide that one. here you can see, so I've just put the optical chip on the back side, and so there would be an alignment issue, right? So how do you get the alignment? So when you're stuffing these optical modules, you might need to go through some sort of active optical alignment. So when you plug in the connector, you get a proper optical alignment. So that would be a manufacturing process there that you need to go through. And then on this other one, if I just hide this one as well. Here we've got they're on this side of the board, and we've just got a hole through the board with the optics coming through it here. So that could then drive into a passive optical cable there. So I mean, this is very cartoony, but the idea here is we can start to introduce optics, and we don't have to go all the way to co-packaged optics, and it might be easier to go to this near packaged optics, and this could be a half a picojoule per bit interface, maybe, and then if you've got a picojoule per bit optics, you know, then that's quite a low power optical cable that could go up and down the data center. So that's that. Any questions on that? Again, if you're a photonics expert, you can drill into me now. Okay.
Maybe another question, like not about the optics, but just from my understanding, you're talking about these rectangular black connectors. Those would deliver power and data, or power or data, if you're staying in the electrical domain, like this MCIO.
So the MCIO, it doesn't. The power to the module comes from the. Let me switch back to that. Comes from these two pins here. These are the 48 volts in the module. It's a blind mate. When you plug the module into the wall provides 48 volts of power and provides the water or the coolant to cool the module. Okay. And then now you will need power to power these media. So the 48 volts will get transformed down to 12 volts, and the 12 volts will feed these modules here. And there's something I'd love to do on the 12 volt world that if we could get the standards people to change. But anyway,
and so those are the little chips right there in between, like those are that's what transforms the power from 48 to 12.
So no, sorry. These are sideband management chips, which would be I'm working with Lattice on. So this is that would be more of the fabric management. But no, the power. Sorry, I've not shown the power. I showed it in the PowerPoint, but it would be in these regions here would be your power, like it is on a traditional OEM. Or you could potentially put power between the devices if it made sense too. So the power is not shown, as in the point of load power is not shown here.
I see. Okay, and so you're saying those pins that are poking out, like on the outside, they would drive the power, but like that same pin it would be hollow and also bring the water, or is that a separate one? No.
So let me go back to the PowerPoint presentation.
Good question. Sorry, I'm just trying to.
That's fine. There was a lot to take in. So here's a module with its little water chassis around it, and so these connectors here are the water coolant. So 2 inlets, 2 outlets. They're blind mate as well. So if we all live in houses, right? And we all have walls, and guess what's in those walls? Water and power. So it's saying, why don't we just take that idea, and so the water and power is provided by the wall, and it's 48 volts. So it's a super with big fat bus bars, or you'd have local power supplies stepping down from the data center voltage levels of 370 volts or whatever that is. So I've been talking to OCP Regional Summit. I talked to Murata. They do the step down to 48 volt power supplies. So they're in our work group, just seeing how they could build that into the wall, and we could get efficient power delivery. So, but yeah, so the 48 volts comes in extremely efficiently, and then you step down from there.
Makes sense. Okay, thanks.
So really, I've only got a summary slide now, so let me just switch to summary slide. So yeah, so I think we've got an opportunity to create a chiplet enablement platform around HPCM. That's my I guess my call to action. Is that a possibility? And if we do, HPCM, you know, outside of just the chiplet enablement, it brings multiple sustainability benefits. It's simple and effective heat energy recovery and reuse for reuse. It improves the power delivery efficiency and the power integrity. It improves the brings signal integrity benefits, which can be both energy efficient, like we discussed earlier, where we could reduce the picojoules per bit needed to drive the shorter distances, or we could transmit over longer distances without retimers, etc. And we can use less raw materials, so we improve the infrastructure's carbon footprint. And I guess I'm not sure how many of you are aware of Raspberry Pi community, or the maker community of the embedded world in the IoT world. But we're trying to create a maker community for high performance compute and for CXL enablement. And now I'm saying maybe we could make this a maker community for chiplet adoption if we tried to rally around this substrate, which was clearly scalable into some significant size computers, and maybe even an HPC cluster at some particular point. So I guess that's my hope and desire from this, is that you guys say, yeah, let's just use HPCM as our go-to substrate. Maybe we get to a tile type architecture, and maybe this can help the business case and the success and traction of the chiplet approach. Thanks very much, guys. So any more questions on that? Any more comments?
I had a question on those modules. What is actually available? Are people already producing memory and switches and CPUs, or this is just at the concept stage? Yeah,
these modules here. Yeah, yes. So the overall module is at the concept stage. These modules are real, and I think Michael Choi is on, but Michael's a member of our group. But Samsung do a CXL.mem. They do. They've got what they call smart memory and smart SSDs. So there's CXL. So they've even got CXL-enabled SSDs, and that they include near memory or near computational storages. I think there's a buzzword for it. So you can actually do some level of compute actually in the media itself. So you don't need to move data across the interconnect necessarily. You can do local compute there as well in the media or near the media. And so, yeah, these modules are very much established. In fact, OCP as a whole is moving lock, stock, and barrel. You won't see any U.2 SSDs anymore in the OCP chassis. They're all, if you've seen the recent system announcements, they're all EDSFF related. And then there's a NIC 3.0, which has obviously been in production for a while now, which is in this format as well.
Okay. Yeah.
So the media will exist. It's just the module doesn't.
Yeah, I know we're running out of time, but I think I push Marek to invite you to join the business group or continue, look at the business discussion, because this is quite interesting to me. But we should have a business chat on this. So.
Yeah, and I'll be happy to do that. Unfortunately, I can stay for, if we've got a meeting today, I can stay for the first few minutes, but I will have to run. I've got to be somewhere.
Yeah, we do have a meeting right after at noon Eastern or 9 p.m. 9 a.m. Pacific time.
Yeah, but I do try to come along to those. I'm not very consistent, but now I've left Untever AI, so I've got more time on my hands to focus on this. So I'll be happy to regularly join that.
Okay. Oh, thank you for that presentation. It was really interesting.
Okay. Well, thank you very much.
Does anyone else have questions? Okay, then I guess we can end a couple minutes early, and then, as I said, there's going to be the business call in 8 minutes. We're going to be on in the separate meeting room for the subgroups this time. So just follow the link that you have received, hopefully through the invite, and if you don't, I can also put it in the chat here since it has changed from last time.
Yeah, would you mind sending it out, because I think my notices go to my previous employer, and
okay,
I don't
sounds good. Yeah, let me just grab that right now. No worries. Just finding here the. Okay. That's that. Okay, so I'm just gonna paste the link. Okay, so this is the link now for the business group meeting, which is the same as for any other subgroup now. Okay, then thanks everyone.
Thank you all for listening to me.
Thank you, Alan.
Thanks,
It was great.
Thanks, Alan. Okay, bye.